Castigliano's theorem can be applied to axially loaded members, bending members, and sheared members. The strain energy can be formulated in a very analogous way for all three of these phenomena. For axial, we have integral of n squared dx over 2ae. For bending, we have integral of m squared dx over 2ei. And for shear, we have integral of alpha v squared over 2ag. Alpha being that shape factor. Remember, I showed you that as 1.2 for a rectangular section. So the beautiful thing about the theory in general is that you take the strain energy, you differentiate it with respect to the load, and you get the displacement. I'm going to use the word load kind of loosely here. Load, P, could be a physical point load, or it could be a bending moment. And if it's a point load, then we get delta in the direction of Pi, and if it's a moment, we get theta in the sense of Mi. And there's a head exploding thing here. We could take partial U, partial delta, and then we'd get the load, which we will do. And then there's another crazy thing, is that this actually works for nonlinear material properties as well, which is super cool. So, as I said, if we have a situation where we're looking for a delta and there is no load aligned with that delta, we need to apply a fictitious load. Just remember that you must differentiate first, throw that into the integral, and then you could set that fictitious load equal to 0. So we did that, we'll do that right now. So here we have a cable and a strut. They're of equal lengths, but different areas, different moduli of elasticity. We have a point load P coming down, and we're seeking the horizontal deflection of B. And of course there is no load horizontally at B, so this is the example where we need this fictitious load. So I put a Q in here using a dashed line, and it doesn't matter whether you assume tension or compression for the strut and tie. I assumed compression here. You can hit the pause button and check my statics, but the statics are not the hard part here. Everybody in the room knows how to do that. So I have NBC as a function of P, Q, and theta, and I have NBD as a function of P, Q, and theta. So now what I'm going to do is use this integral, but I'm going to differentiate U, and I'm going to pop that derivative in the integral, and I'm going to use that chain rule, just like last time. So the differentials are very quick. Here they are, 1 over 2 cos theta, 1 over 2 cos theta with a minus sign. And now what I'm looking for is the delta horizontal, and it's the partial, but remember I'm taking, I'm bringing the partial in the derivative, and the same as before, the 2's disappear. So I'm saying this is just like in the previous board notes. We differentiate n, so we'd have 2n over 2 plus partial n partial q, all of that in the integral. So, and we're integrating with respect to x over the length. And the same with n. The 2 pops out in front, the 2 in the denominator disappears, and we have that chain rule. Then we set the q equal to 0, so it's a little simpler, and I evaluate it on the next video.